And welcome to the YouTube channel for Wayne State University's chapter of the Tau Beta Pi Engineering Honor Society. My name is Austin Heitzman. I am a computer science major here at Wayne State, and this semester I'm going to be learning elementary linear algebra, so I figured I would learn it alongside of you guys. So let us start from section 1 of chapter 1. We're going to be talking today about systems of linear equations. Now, on my first day of class, we introduced this topic, and I was sitting there thinking, like, gosh, I already learned this years ago. Why are we sitting here learning something that comes in baby algebra when we're all the way where we are now? Well, the answer to that is that matrices, which are pretty much the core of this course, are pretty much just systems of linear equations when you start looking into it and start learning it. So trust me, our future selves will thank us if we review this now. So, without further ado, let us introduce our system of equations. And it's going to have a general form that looks a little spooky for now. And this is what it's going to look like. Oh my gosh, where are all the numbers? This looks like alphabet soup. But really, this is just a general form, so it's going to start making a lot more sense. And basically, the solution set is going to be something so that x1 is some number, x2 is going to be some number, and however many x's we have up until xn, which is also going to be some number, let's just call it z, for the end of the alphabet. And the idea is that we can plug this number a into all of these x1s, and this number b into all of these x2s, and this number z into all of these xn's, so that all of these answers are true, right? And when we do that, we're going to write it out in a form that's kind of going to look like a coordinate system. So the notation to do this is going to be just these parentheses, b all the way until z. All right, and again, this is going to make a lot more sense when we start doing some real examples, which I promise we will do at the end of this video, but right now I just kind of want to lay everything out for you. So, before we get into the rules, I do kind of want to just touch on what makes this linear. Like, why are we calling this a linear equation? Well, I think the answer is kind of soothing for me. Linear essentially means that each unknown, so all those x1s, x2s, up to xn's, is only going to appear individually. So we're never going to get like a function of x. Remember, this is linear algebra, right? So we're not going to be doing anything like super crazy with this. In fact, excuse me, the only thing we're going to do to unknowns is to multiply them by a constant. Let that sink in for a second. We're not going to be doing anything nuts. It should be kind of a relief if you took the standard course of a bunch of calculus classes before this. So, it's going to be a few different solution types to this. The first is going to be no solution. So these cases are going to be something like if you solve for all your variables and in one of the lines you're going to see 0 equals some number where that number does not equal 0. That doesn't make any sense, does it? There's no a that equals 0 but also does not equal 0, right? So in this case, we're going to say that the system is inconsistent. It's going to be a little buzzword. All right, so in these situations, it's going to be pretty simple, because as soon as you realize that it's inconsistent and you can prove that by saying, for example, that the last line is 0 on the left-hand side and some number that's not 0 on the right-hand side, you're done, right? Now, the other case, one of the other cases I should say, is that there's going to be one solution, right? So this is the case where you're going to have some number x equals a real number a, x2 equals a real number b, just like we saw in that first example, right? So this is going to mean that there is a single value of x1, x2, so on until xn. There's a single value for all of these variables that is going to solve this system of equations, right? Any other value will not work. It's going to be one solution to this system, and that is what we're going to find and put in that coordinate system style. It's not a coordinate system, I shouldn't say that, but it's going to be in that style. And actually, we will get to coordinate systems because it might be a little bit easier to start framing things in that term, but as far as I've seen in this class, we usually don't frame it geometrically for some reasons. Anyway, the last possibility is infinite solutions. The interesting thing about infinite solutions is that if you realize that there maybe are two values of x1 that will solve the system consistently, if there is any more than one solution, then inherently there are infinite solutions. And you're going to realize that it's infinite solution if you get something like 0 equals 0, right? So the left-hand side, you can boil it all down so that it equals 0. And on the right-hand side of that same equation, it is already defined to equal 0, right? So inherently, that is true, which means no matter what you plug into there, you will get an answer, and it will work. So in these situations, we are going to be introducing something called a free parameter, which, at least for me, that is where some of this started getting a little bit new. Just to give an overview, basically what that entails is taking the last variable and setting it, giving it a name to some other variable that we ourselves are introducing, and then putting all of the other variables in terms of that variable, and so on. So we will see that in one of our examples, but I just wanted to give you an idea of what that looks like. So let us actually pause and look at, like, what does all of this mean? You know, I mean, it's good to kind of know what we're doing, but if we don't have something to anchor us into, like, so-called real world, then it might get a little bit difficult for us to really see what's going on here. So let's just take a momentary break and look at this in terms of coordinate plane. Yes, we're going to go all the way back to geometry. So, say I have this coordinate plane, got the x and y system. We're just going to look at two variables because, frankly, drawing a 3D graph is very difficult for me. So, let's say that we have one line that goes like this, and we got another line that goes like this, right? I want you to pause and think for a second based on what we just went over. If each equation in our system of equations represents a line, right? So, just going to put this in a standard line form that we all know and love so dearly. If each of these represents a line, then based on what we just saw, what type of solution would this graph have? Would it have no solutions, or one solution, or infinite solutions? Well, there is exactly one point on this graph where x and y will produce the same solution. the x point and the y point will satisfy this system of equations simultaneously. So something like this is going to be our one solution category. There's only one solution to this system of equations which will make this consistent. On the other hand, I'm just going to go off to the side here to draw another coordinate plane. That's not a z, that should be an x. Let me fix that, because again, we're just doing 2D at the moment. Okay, say that these lines, I'm going to call them parallel. Let's say they don't even know each other. They have no idea that the other one exists, right? So going back to this idea that each equation in our system of equations represents a line, right? But these lines, there is absolutely no place in these lines where x1 equals x2 and y1 equals y2, right? This does not happen, ever. So, this is where there's going to be no solution. And y'all are smart cookies. I think you can tell where I'm going with this. But just for completion's sake, let us look at the final case scenario. We got one line going here. And due to imperfect drawing skills, this might not be quite exact, but I hope you get the idea. This second line is right smack dab on top of the first one. One could say they are the exact same line, right? In this case, this first y equals mx plus b is the same as big ol' equals sign, the second one. This is going to mean that for any xy coordinate that lies on the pink line, the same xy coordinate will lie on the green line, right? Any solution that you can plug in to this equation will also satisfy this equation. Notice that it doesn't mean that this point satisfies that. It doesn't mean that this point satisfies that. It's not necessarily saying that any old solution in the whole wide world will satisfy this equation. Only that. On this line, you can say that there are infinitely many points, right? This line goes forever and ever in each direction. So essentially, there will be infinite solutions. Now, I hope this helps kind of like put this in a good frame of reference. The annoying part about this is that we're going to be getting into some pretty complex systems. I mean, as you can probably see from our first example here, like this can go all the way to some number, right? I mean, hypothetically, we can have 100 different variables. I would love to challenge you to draw me a graph in 100 dimensions. You know, it's not feasible. So really for this course, we are going to be looking at this from like the algebraic perspective of like actual systems of equations. I have not yet had to draw any sort of graphs for this class. Perhaps that will change in the future, but I don't foresee it. So we are just going to stick to the algebraic version, but maybe it will help to kind of anchor yourself in this idea of a geometric representation. Okay, so now that all that's behind us, we need to know, how do we get these solutions? We are basically going to be using a method called Gaussian Elimination, after some guy named Gauss who invented it. Thank you kindly. And this is going to have 3 sort of legal moves, right? We're going to go through these one by one. They're pretty straightforward. The last one did kind of trip me up for first, so I might spend a little bit of time talking about that. But basically, the first one is we can interchange two equations, right? So if we have a system where this is equation 1 and this is equation 2, we can do an operation so that equation 2 is on top and equation 1 is on the bottom. And this might seem a little useless right now, but trust me, this is going to be very helpful. So right now we're just establishing, like, this is equivalent to this. Oh no, sorry. These are the exact same things, so that is totally fine to do. Another thing you can do is you can multiply a constant throughout one entire equation without changing that equation. So if we have E1, which is just the first equation, we can multiply that. Actually, I'm going to make that an equal sign to show that multiplying E1 by some number is going to make it the exact same thing. We got to do this on both sides, right? So the right-hand side, we're going to multiply by A, and the left-hand side, we're going to multiply by A. But otherwise, this is legal, okay? Now, the last one is something that again, tripped me up a little bit at first. So say we have equation 1 and equation 2, right? We can add, say we want to, it kind of combines this one with adding, right? So we can do an operation so that you can add E2 to E1, and that will become your new equation 1, right? And I'm going to emphasize that because you can essentially thinking of this like adding a multiple of one equation. So think about like adding like a multiple of 1 to E2, and then we're going to add that to E1. Similarly, it can be 2 times E2 plus E1. It's going to equal E1. What I don't want to do, I don't want to say going to multiply the first one by the second one and make that equal to the first one. And I know that kind of seems a little trippy, but that really did get me into some trouble at first. So I would just recommend, if you want to do like a call to multiple of the first row and then try to add it to the other one, just do them separately because it will save you a lot of headaches. So this we don't want to do. These guys are fine. All right, this is very abstract so far. I appreciate your patience as we get through this, but let us finally look at some concrete examples. Okay, so this first one looks a little scary, but I promise we can get through it. The idea for this is we are going to want to start by this first column, right? We have this first one that's just x, right? Now that is perfect. That is an ideal, I'm going to later call it our pivot value, right? But for now, we can use this equation 1. Perhaps I can, just to give you some context of what I was talking about earlier with the E1, C2, C3s. We can use equation 1 to then eliminate all of these, right? We don't want these anymore because then that's going to make it easier for us to solve for the next variables, right? So let's try to use some of those rules that we saw before, right? So if we're going to use equation 1 to eliminate the first values of the rest of the equations, how can I do that? Well, first thing I notice off the bat is that this guy is just the inverse of this, right? Not inverse, but it's the opposite, right? X and negative x. If you just add E1 plus E4, well, that's going to cancel this out so that that's going to be 0, right? So we can make that our new equation 4. Similarly, for the equation 3, our second step, we can take equation 3 and subtract it from E1. Now, I know we did not say anything about subtracting in our rules, but if you think about that, all we're doing is adding a constant multiple of -1 to equation 1, and then adding that to equation 3, right? Because saying like E3 minus E1 is the same thing as saying E3 plus negative E1. So this is also legal. So we're going to make that our new equation 3. And in the same light, what we can do for equation 2 is say equation 2 minus 2 times equation 1 is going to be equation 2, right? And notice here, all I'm doing is laying out. I'm looking at this, I'm looking at the system, and I'm seeing how can I manipulate this. I'm just going to plan out all of my steps for the first column, and then I'm going to execute them. So we're going to have to write this whole system out again. I'll change the color so that it's not too confusing. Now this first equation, we're manipulating it in terms of these steps. However, the equation itself is not actually going to change in practice, right? We're just kind of using it. So this is still going to be our equation 1. Let's start at the bottom because that's going to be the simplest one. So x plus negative x is going to be 0, right? We have successfully eliminated that. In the same way, we have -1 minus 5. So I'm going to have a minus 6y. With 2 minus 12. So that's going to give me a negative 10. And then we have to do the exact same thing to the answer side, to the right side of the equations, because otherwise it's not going to work. So we have 5 plus 4, and that's going to give you 9. Now it seems like going painfully slow, but I want to remind you that one tiny little mistake in this will throw off the entire thing, so it takes less time to go slow. Okay, similarly, we can do the same thing with 3. We're going to take equation 3 and subtract it from equation 1. So x minus x is going to be 0. I have 8 minus -1. It's going to be a 9. But -1 minus 2, so -3. And the variables are just going to stay the same, obviously. And then we have 3 minus 5, it'll be a -2. All right, now this last one might get a little tricky, and if you need to like write the steps off to the side, that's of course totally fine. But I'm going to see if I can just do it on the fly. So we're going to take equation 2 and then subtract 2 times equation 1. Actually, you know what? Just so we're all on the same page, let us in green up here. So if I multiply equation 1 by -2, that's going to give me -2x plus 2y minus 4z equals -10, right? And again, this is not like anything that we need to be writing into this system since we're just using it, but it's going to help me when I'm actually trying to solve this so I don't make any silly mistakes. So adding these two together, you can see that these are going to cancel, so that's going to give us 0. 1 plus 2 is going to give us 3y. We don't have anything here, so that's -4c. Then 2 minus 10 be -8. All right, now see what we've done here. We have just eliminated this whole row so that we don't need to worry about these x's anymore, right? So what's next? We do the same dang thing for this one right here. Now I have this guy, and I want to use that to eliminate these. So let us see if there might be a way to do that without making any rationalizations. Yes, there certainly is. So, since 9 and 6 are all multiples of 3, we can definitely make this work. So, our first step for this row, so I'm just going to start labeling this 4, is going to be, how can I eliminate positive 9 using a positive 3? Well, I can take equation 3, I can add it to a negative 3 equation 2, and that's going to be equation 3, right? So I'm basically going to multiply everything in equation 2 by a negative 3, and then those will cancel out. Similarly, we'll do the same thing with equation 4 with a multiple of positive 2 on equation 2. And doing that in the exact same way that we did the first time. Remember, equation 1 is not going to change, so I'm just going to copy it down. This time, equation 2 is also not going to change in principle, so I can just copy that one down. We're just kind of working our way down the list, right? Now, for the first run, let's off to the side, I'm going to multiply everything by negative 3. So that's going to give us a negative 9y. Negative 3 times negative 4 will be a 12z. Negative 3 times negative 8 will give us a 24. Yes. All right, so, and we're just going to write this here just so I can do the addition. I'll erase it in just a minute. All right, so this first one is going to cancel us out, which is exactly our goal. That's why we're doing this all in the first place. From there, the z term is going to be a positive 9. And then the solution is going to be 22. 24 minus 2. Similarly, for this equation 4, if I multiply everything in equation 2 by positive 2, our new equation is going to look something like this. At least I certainly hope so, unless I did something grievously wrong. But I don't think I did. Let's find out. We have 0 in the first term. That is exactly our goal. From there, it's going to give us a negative 18z. And then negative 16 plus 9 is going to be a negative 7. All right, we have done what we have came here to do so far. Oops. We have eliminated these terms. Now, from here, we can take another step and try to use this guy as the sort of pivot to get rid of this, right? Once again, I see that 9 is a multiple of 18. So I am just going to say equation 4 plus 2 times equation 3 is going to give me equation 4. We're going to notice something happen here. After I copy down everything, and yes, we need to copy it down every time, you're going to get really comfortable with writing. This time I can just copy down the third equation because we're, again, just using it, right? We're not actually changing it when we do things like this. Now, 2 times 9 is going to give us 18, so that is going to give us 0, right? But 2 times 22, right, minus 7 is not going to give us 0. It's going to give us, I don't know, 37, some number that's not 0. And that's all that matters. This, inconsistent. You know what that means? Is that there is no solution to this system. And that's all we need to do. As soon as we see that you have 0 on one side and a different number on the other, we're done with that. So, let's take a breath, because I know that was a lot. But let's try another one that's going to have a bit of a different result. I'm going to go a little bit faster now that we have kind of the idea lined up. But if you need to kind of pause the video and start jotting this down, or start trying to think of how you would do it on your own, I encourage you to do that. So just like the first time, we're going to try to eliminate this, right? It's only 3 equations this time, so it's definitely not going to take us as long as the first one did. So again, let's try to think of planning your steps before you dive into this. I see that equation 1 plus equation 2 is going to eliminate that first negative x. So that's exactly what I'm going to do for my step 1. E1 plus E2 is going to give me E2. And similarly to what we did last time, I see that if I take equation 3 and add it to -2 times the first equation, so I'm going to say E3 minus 2E1 is going to give me my new E3. Let's try to write all of this out, and you'll notice that I'm laying all these steps out only insofar as it will eliminate that first column, right? We're going to work column by column until we can get ourselves to a point where we have a solution, or can at least determine that there is none. So the first equation is going to stay the same. Second equation, we're just going to add the first to the second. X minus x is going to be 0. Y minus y is going to be 0. Z plus z is going to give me 2z. And 4 plus -2 is going to give me a 4. Likewise, we have, again, I'm just going to do this really quick multiplication to the side, just so I don't make any stupid mistakes and look dumb on the internet. It's going to give us -2x plus 2y minus 2z equals -8. So that first term is going to cancel to 0. I have 2y minus y. It's going to give me plus y. -2z plus 2z. And then -8 plus 2 is a -6. Now this one is kind of working out in a pretty nice way. Actually, if we wanted to make this even easier to view, we can use one step that we haven't seen in practice yet, which is going to be that first legal move that I mentioned. You can interchange equation 2 and equation 3, excuse me. So doing that, we're going to see equation 1 is going to stay the same. Y equals -6. You'll notice I can just leave a blank space where the zeros are. So now this is going to show that we got that nice like diagonal formulation. This is more of a convention for now, but it does kind of make it easier to see. And this, clearly, you are going to have a solution to this, right? I mean, we have 3 equations, we have 3 variables, and it looks like everything's going to line up. So we can just start solving now, right? I'm going to start from the bottom, especially because usually there will be some number right here, so we're going to need to like work from the bottom up. So 2z equals 2. So that means z equals 1. I'm going to box this in just so I can very easily see. This second equation, super simple. It's literally given right to us already. Y must equal -6. And for this top equation, now we're going to use what we've already found as y and z to find x. So I'm going to say x minus 6 plus 1 equals 4. So that's going to be x minus 5 equals 4. X is going to equal 7. All right, we have one solution here. That solution is going to be in the form of 7, -6, 1. And it turns out I did misspeak earlier, because if you think about this as a coordinate system, what did we just do? You know, we found that there are 3 lines in the 3D plane. First one has this equation, second one has this one, third one has this, and we have found a point where all of those 3 lines intersect. How cool is that? And to check this, one of the things I love about linear algebra is that it's super easy, and it works to actually check your work. And to do that, all you need to do is plug in the results to these equations and make sure that they all do in fact equal those things. I'm going to leave that as an exercise for you, because this video is already running long and I wanted to cover one more example. But I do encourage you to do that, and if I somehow misstepped and got the wrong answer, then that will be something that you will be able to see as well. Okay, let us try just one more here. This is going to be, if you can't tell, just based on the structure of this video, this is going to be one of those infinite solution types, and we're going to be able to see how to use that free parameter instance that I referenced at the beginning. So if that part confuses you, then this is definitely the one that you want to try to stick around for. So we're going to do the exact same thing as what we did. The nice part about this one is that we already have this eliminated for us. There's nothing here to begin with. So I'm just going to go straight on and try to eliminate this guy, right? Similarly to what we have just done a couple times now, I see that if it's actually going to be easier, instead of having to divide one row by another to get this to equal 4, because I need to manipulate this row so that I can change this one, right? So what I'm going to do is I'm actually going to flip these around. I'm going to use that first rule that we can do. And it's not strictly necessary. The cool thing about this is that there are many ways that you can solve these systems, but it just really matters on like what's easiest for your brain to see. Pretty much as long as it's like a valid solution, then you're going to be fine. So I'm just going to rewrite this out and swap those 2 equations. Sorry. Squared. Make sure I did everything right. Not like that. Yes. Okay. So from here, what I can do is I can multiply this second equation by a -2 so that this is going to equal +8. And then when I add it to equation 3, that's going to cancel out this guy right here. Yeah? So let's give that a try. I'm going to have, and for consistency's sake, I will write that out as soon as I am done here. So I'm going to take equation 3 minus 2 times the equation 2, and that's going to be equation 3. Alright, so I am going to do -2 times -4, that's going to give 8x2, -2 times -4, again 8, minus 24x4, -2 times 8 minus 16. Okay. The home stretch, folks. We got this. Alright, so we're just going to do that addition for the equation 3, but that also means that we can just copy down equation 2. In essence, this is not changed. Alright, so this is going to give me 0 for the first term, 8 minus 7 is going to give me just 1. Negative 24 plus 22, going to be a negative 2x4. Negative 16 plus 17, just going to give me 1. All right, so we have eliminated that. And we got that nice diagonal form. Now, there is no other equation for me to use in order to eliminate another x3 and get this fully in form, right? We have more variables than we have equations, which is going to be significant as we start doing more of these. But for now, something I notice is that there's nothing more that I can do to try to actually get like a solid number answer, right? Now, back in the day, we might have just been able to say, okay, well, there's nothing more we can do. There's no solid answer we can get, so we're done. But nowadays, we are going to introduce our free parameter. It's standard convention to use the last variable, which in this case is going to be the x4. So what I'm going to do is I'm going to take x4, I'm going to call it out as special, and I'm just going to name it. I'm going to name it t. Now, this seems silly and insignificant, but what we have done is we have said x4 can be whatever the heck it wants to be. It is not dependent on any other variable. It can do whatever it wants, right? So now we have these other variables. They are not free, right? They are going to depend on whatever x4 is. So we can use that. We can use the fact that x4 is just t in order to solve for the other variables, right? So x4 is now solved. I'm going to box that in. x3, let's use this last equation. We have this last equation saying that x3 minus 2x4 is 1. We've already solved for x4. x4 is now 2. So I'm going to plug, x4 is now t, not 2. I'm going to plug t into the x4, into this equation, and just solve for x3. That's going to mean that x3 is going to equal 1 plus 2t. That is your solution for x3. So on, we can use the second equation to solve for x2 by plugging in x3 and x4. Notice we're doing the exact same thing as we did for the one solution, only we're just using a variable this time. So I have negative 4x2 minus 4 parentheses, so we don't forget to distribute, plus 12t plus 8. And this is solvable, right? Minus 4 minus 8t plus 12t equals 8. Can 12 minus 8, 4t, and then I can add 4 to both sides to give 12. Negative 4x squared is now going to equal 12 minus 4t, and we can divide by negative 4. x2, what is that? 3 plus t. Unless I've just did a brain fart, but I guess we can find out. Okay, so now we just have the one more to solve for x1. Forgive my scrolling here. Plus x3 is 5x4 equals negative 1. Right, so we can use x3 and x4 to solve for x1. It's 1 plus 2t minus 5t equals negative 1. x1. Subtracting that will give me a negative 2 on this side. Negative 3 will add to a 3t. 3t minus 2. Does that make sense? Yes. Yes, it does. Okay. So I know it looks a little weird, but we have our answer. Now our answer in coordinate form is going to be 3t minus 2, because that's our x1 term, negative 3 plus t, x2, x3 is 1 plus 2t, and x4 is just t, where t is any real number. Yeah? Look at that. Alright, and again, that looks crazy, but you can check your work in the exact same way by plugging these into this. All of the t's will cancel, and you should be able to get the answer that you're looking for. And again, I'm not going to do that in this video because we're already running quite over, but I definitely encourage you to use that as an exercise. So thank you so much for sticking with me through all of this. I hope we've covered some really good things. I encourage you to kind of rewatch this if you need to, kind of pause it at certain places to see if you can try to start to figure some things out on your own. This is going to play greatly into matrices, which we will be covering, I think, in the next video, actually. So I encourage you to review this as much as you can before then. Thank you for watching. I hope you subscribe to this channel if you're interested in more tutoring videos for any engineering field, and we will see you next time. Thank you.